Good morning, students. Up till now, we see the application of CFT to octahedral complex and square planar complex. Now, we are going to see application of CFT to tetrahedral complexes. That is coordination number 4. A tetrahedral arrangement is the configuration in which the link and repulsion is in the list for 4 coordinated metal ion. Further, this is the configuration expected for a complex with a radius ratio of cation and the anion is in between 0.225 and 0.414. The directions of approach of the ligand do not coincide exactly with dxy, dyz, dxz orbitals. That means it is in between the direction of the axis. The 4 ligands in a tetrahedral complex can be considered as arranged at the alternate corners of the cube and the metal atom at the center. The directions x, y and z points to the center of the faces of the cube. The easy orbitals points along the x, y and z, that is to the center of the faces, and T2G orbitals points in between x, y and z axis, that is towards the center of the edges of the cube. See in the figure particularly at the center, and there is the x, y and z directions, and ligands will be approach along the x, y and that particularly in between that directions. The directions of the approach the ligand do not coincide exactly with the either easy or T2G orbitals. T2G orbitals are near to the directions of the ligands than easy orbitals. This is shown in the particularly figure. See dx position of or the particularly lobes positions of the dx square minus y square, dz square, dxy, dyz and dxz orbitals. The approach of the ligand raises the energy of both T2G and EG sets of orbitals, but since the T2G orbitals are closest to the ligands, their energy is raised mostly. The crystal field splitting is in the opposite way to that of the octahedral complexes, because in octahedral complexes the ligand are approaches along the x, y and z axis, but here they are in between the x, y and z axis, so the splitting is completely opposite. The T2G orbitals are 0.4 delta T opposite the average energy level, and the easy orbitals are 0.6 delta T below the average energy level. This occurs in the figure. The magnitude of the crystal field splitting delta T in a octahedral complex is considerably lower or lesser than the octahedral complexes. Other things being equal, the crystal field splitting delta T in a tetrahedral complex is approximately 4 by 9 of the crystal field splitting in an octahedral complex. Thus, delta T is equal to 4 by 9 delta O. It is also the case in a tetrahedral field that the total increase in energy of T2G orbitals are both the average level is completely balanced by the total increase in energy of the easy orbitals below the average level. The difference in the energy between EZ and T2Z is shown as delta T or 10 dq. In tetrahedral complexes, the electron pairing energy is generally high. It is more stable than delta T or 10 dq. So electrons generally enter the orbitals with parallel spin. In other words, tetrahedral complexes are always high spin complexes. The crystal field splitting being small in tetrahedral complexes. Tetrahedral complexes are not expected to be low spin complexes. Irrespective of strong and weak ligand field, the tetrahedral complexes are more likely for non-transition metal and transition metals with no crystal field splitting D0, D5 and D10. There is crystal field stabilization of the tetrahedral complexes of D2, D4 low spin and D7 ions. However, in some cases, the crystal field stabilization of octahedral or square planar complex can be even greater. See the CFAC of our high-spin tetrahedral and octahedral complexes. We compare here both the CFAC for tetrahedral and the octahedral. The number of d electrons if 0, 5 and 10, tetrahedral and octahedral both have 0 CFAC. For the electrons 1 and 6, for the tetrahedral CFAC is 0.6 delta T. When we convert it into the octahedral, it is 0.27, and for the octahedral it is 0.4. So see, when we calculate the CFAC for 1 and 6 electrons in the orbital, at that time tetrahedral have the lower splitting while octahedral having the higher splitting or delta O values. When 2 and 7 electrons in the orbital, tetrahedral shows 1.2 delta T. When it converts into delta O or for the octahedral, it is 0.53. But actually for that octahedral complexes, it is 0.8 delta O. Similarly for 3 and 8 electrons, delta T is 0.8 delta T. It is converted to the octahedral field, it becomes 0.35 delta O. But actually for the octahedral complex, it is 1.2 delta. For 4 and 9 electrons in the orbital, tetrahedral CFAC is 0.4 delta T. It will be get converted to octahedral, it becomes 0.18 delta O. Actually for the octahedral, it is 0.6 delta O. Thus there is difference in CFAC for tetrahedral and the octahedral, and this indicates that always tetrahedral splitting have the lower extent or the lower field than the octahedral complexes. In the octahedral and tetrahedral complexes, both the CFAC for D0, D5, D10 arrangement is 0. In all other cases, the octahedral CFAC is greater than the tetrahedral CFAC. We see this particularly in the last stable, and we can got the particularly difference in the CFAC. Here particularly the octahedral complexes are generally more stable and more common than the tetrahedral complexes. This is because there are 6 ligands energy terms rather than the 4, and partly because there is the larger CFAC terms. Tetrahedral complexes are favored in the following conditions, where the ligands are large and bulky and could cause the crowding in the octahedral complexes. When the ligands are weak, so that low in CAPC when low, it favors the tetrahedral complexes. Where the central metal has low oxidation state, since this reduces the magnitude of delta values and it favors the tetrahedral complexes. Where the electron configuration of the central metal is 0, D5, D10, since there is no CAPC, or D1 or D6, where the loss in CAPC is small, then it favors the tetrahedral complexes. Some complexes of the tetrahedral situation or systems are TiCl4, MnO4 1 minus, FeCl4 1 minus, COCl4 2 minus. They favors the tetrahedral complexes. Many transition metal chlorides, bromides and iodides form tetrahedral complexes. Further, large ligands or those with the negative charge mainly favors the octahedral complexes to minimize the ligand-ligand repulsion. Oxyanions and the chlorides form such complexes. Examples of the such complexes, that is AlCl4 1 minus, TiCl4, MnO4 1 minus, CrO4 2 minus, FeO4 2 minus, FeCl4 1 minus, COCl4 1 minus and ZnCl4 2 minus. They can favor the tetrahedral geometry.